right, so let's start at number 1A here. All right, so here we're starting with some basic exponential equations. These, of course, are the same base equations, so we want to get these bases the same. All right, obviously we can't change 3 any, but 27 we can change to 3 cubed. And of course our exponent stays the same. All right, well now that we have this power to a power, we can go ahead and multiply. Do remember that you have to distribute to both of these. So this will end up being 3 to the 6x minus 3 power. And then this, of course, is still just 3 to the 4x plus 1. All right, once we have it like this, where the bases are the same, all right, we can simply set the exponents equal to each other. So we just say 6x minus 3 has to be equal to 4x plus 1. Now we solve this like any algebra 1 equation. So subtract 4x from both sides, add 3 to both sides, divide by 2, and we are good to go. All right. We do similar over here. All right. Since these are obviously both able to do 8, you could do 2 as well. You could change this to 2 cubed and this to 2 to the negative third power. All right. But we don't have to. They're both 8, so we can just leave this as 8 to the 2 minus x, and this is 8 to the negative first power. Now that our bases are the same, we can just set our exponents equal to each other. All right, so subtract 2 from both sides. So x has to equal 3. And continue on, same concept. All right. So here, 25 can be rewritten as 5 squared, and 125 can be rewritten as 5 cubed. Again, we just go ahead and multiply our exponents here. So we're going to get 5 to the negative 8x plus 6 is equal to 5 to the negative 3x. All right, so again, we can just set our exponents equal to each other. We can add 8x to both sides, divide by 5, so x is equal to 6/5. All right, D, same thing. 8 can be rewritten as 2 cubed. 16 can be rewritten as 2 to the 4th. So we do our multiply our exponents, and I'm just going to jump straight to setting the exponents equal. So here we will get 9x, and here we will get 4x minus 4. Subtract 4x from both sides, divide by 5. So x is equal to negative 4/5. All right, so now we have some equations in logarithmic form. All right, we do always want to keep our definition of logarithm kind of handy, right? So log base b of a is equal to c if and only if b to the c is equal to a. All right, so here this is in logarithmic form. We want to switch it to exponential form. So that would be 5 squared is equal to x. Well, 5 squared is just 25, so x is equal to 25. For letter F here, do remember that ln is simply log base e. All right, so now we can write this in exponential form, and we will get e to the 12th power is equal to x. And on the non-calculator portion, just leave it like this. All right. There's nothing else you can do without a calculator. All right, same concept. All right. Here we're going to say 12 to the x power is equal to 1 over 12. Well, here we just kind of have to use some common sense and reasoning. All right. Obviously, to get a fraction, this has to be a negative exponent. All right. So here x is going to be negative 1. All right. Here, now you could just kind of understand that ln and e kind of cancel each other out, but if you want to strictly use alright, so you could do definition of logarithm again and say e to the 13 equals e to the x, alright, or we also had a property that said log base b of b to the x equals x, so we would know that these just kind of cancel out and x is equal to 13. Now, if you don't like that idea, then go ahead and use your definition of logarithm, and you get e to the 13 is equal to e to the x. Well, now this just became a base problem. Well, now that our bases are the same, we can set our exponents equal to each other, so 13 equals x. So either way, you get to the same conclusion. All right, kind of same concept here. All right, e and ln are going to kind of cancel again, so you could just say x is equal to 28. But if that doesn't make sense to you, just go ahead and use definition of logarithm again. Even though there's an ln here, because it's in the exponent, this is actually an exponential form. So we would say log base e of 28 is equal to ln of x. All right, well, log base e is just ln, right? So if ln of 28 is equal to ln of x, right, this is another one of those properties that we talked about. If ln of x is equal to ln of y, then x must equal y. Right? Well, obviously, in order for these two things to be exactly the same, x has to be 28. All right, same concept over here. If log base b of x is equal to log base b of y, then x must equal y. So I can just set my arguments equal to each other here. Don't want that. So x plus 4 is equal to 9. So x is equal to 5. Pretty straightforward there. Same concept here, but we do have to take this 4 out here first and move it up as an exponent. Right? So we will have log base 3 of x is equal to log base 3 of 2 to the 4th power. All right, again, since log base b of x is equal to log base b of y, then x must equal y. And of course, 2 to the 4th power is 16. All right, here these are separated by a plus, right? They're not separated by an equal, so we can't just put these things equal together. A lot of students try to do that. All right, we use our other properties of logarithms where we expand and condense, right? And when we have two different logs with the same base separated by a plus, we can write them as a single log and simply multiply the arguments. So x times 3 is simply 3x. All right, well, now we can write this in exponential form using our definition of logarithm. So this would be 6 to the 1st power is equal to 3x. Of course, 6 to the 1st power is just 6. We can divide both sides by 3. So x is equal to 2. All right, now it wants us to convert here from logarithmic form to exponential form. Again, we are simply using our definition of logarithm. All right. So here, remember, ln is simply log base e. All right. So it looks like this. I want to rewrite it like this. This is simply e to the x equals 25. And that's it. You're done. You don't need to solve for x. It just says to write it in exponential form. This is it. You're done. All right. Similarly, this is written in exponential form, and now we're going backwards to log form. So this would be log base 8 of 122 is equal to x. It's in logarithmic form. You're done. You don't have to do anything else. This is just a simple exercise of converting between logarithmic and exponential form. All right. Now it wants us to find these things. All right. So it's like, okay, what does this equal? All right. We can write it in exponential form. So we get 8 to the question mark is equal to 32. All right. Now, you could use X here. You can use smiley face, dollar sign. It doesn't matter, right? It's just a placeholder, right? But now, a lot of people get stuck here. We can actually just think of it like the very first problems we worked on, the same base equations, right? So I can rewrite 8 as 2 cubed, and I can rewrite 32 as 2 to the 5th. All right, well, now we can multiply our exponents, and then since our bases will be the same, right, we'll have 2 to the 3 question mark is equal to 2 to the 5th. So 3 times question mark equals 5. So question mark equals 5/3. Again, you could have just made this an x if you want. All right, here you could kind of set it to an equal sign and go through changing it to exponential form, and then you'll see that it works out quite nicely. But we have a property that says if you have log base b of b to the x power, that just equals x, right? So this literally just equals -31. All right, so you are perfectly able to just do that. But if you want to do it the long way, right, let's set this equal to x. All right, and now we can change this to exponential form. You would get 5 to the x power is equal to 5 to the -31st power. Well, again, obviously, since our bases are the same, you can set the exponents equal to each other, and voila, we are done. All right, here is expanding and condensing. We'll start with expanding. All right, so write log of the cube root of m times n to the 5th all over p to the 8th times q to the 4th in terms of log m, log n, log p, and log q. All right, so do remember that the cubed root of m in this case is simply going to be m to the 1/3 power. All right, so I'm going to go ahead and break these apart using the product and quotient properties first. All right, so I'll be able to say, okay, well, this is log of m to the 1/3 plus log of n to the 5th. All right, now I put plus here because these are both on top. Down below, since they're being divided, I'm going to subtract log of p to the 8th minus log of q to the 4th. All right, now, some people think of these as being multiplied, so they like a plus between them. That's fine if you put the whole bottom piece here in parentheses, because then you essentially would just be distributing that negative, and that would be the same thing mathematically. I just think of if it's in the top, it's positive. If it's in the bottom, it's negative. All right. Well, now we're going to go ahead and use our power rule, which says I'm allowed to take these exponents of the arguments and bring them out front as multipliers. So this will be 1/3 log m plus, I can bring this 5 out front, 5 log n, I can bring this 8 out front, minus 8 log p, I can bring this 4 out front, minus 4 log q. Alright, so that is it. We are done. Alright, now we're going the other way. Alright, we're going to condense this into a single logarithm. Do notice that word single. Lots of students try to still throw in 37 logs here. Alright, please do not be one of those students. Alright, so I'm just going to do the opposite of what I did last time. First, I'm going to move all of my out fronts here up in as exponents. Alright, so I'm going to start with log of a cubed minus log of b to the 3/4 minus log of c to the 5th plus log of d to the 8th. All right, so now I'm going to go ahead. Now do be mindful, just kind of off to the side, this b to the 3/4. And we talked about fractional exponents before, all right? So remember the denominator is actually a root, all right, and the top stays a exponent. So that's going to be the 4th root of b cubed, all right? Well, now, kind of like the opposite of what we did in the last problem, anything with a positive leading coefficient, the argument is going to stay in the numerator. Anything with a negative leading coefficient, the argument is going to stay in the denominator. All right, so this is going to be equal to log. All right, up top, I have an a cubed, and I have a d to the 8th. All right, down below, I have a b to the 3/4, which I know is really this. All right, and I have a c to the 5th. And that's it. We are done.
What is the least correct if we wrote b to the 3/4 instead of b to the 4th root of b to the 3rd?
I would probably take like a half of a point off. You would still get like 7 of the 8 points, or actually 7.5 of the 8 points for this. So you would get a little tiny fractional point off, but 7.5 out of 8 is still an A for that problem. All right, so now we're going to jump to the calculator portion. All right, so here, very hard for us to do. So again, we want to use that definition of logarithm and rewrite this. And this would be rewritten as log base 7 of 50/50 is equal to x. All right, well, now, all right, we can have to use our calculator for this part. You can use the change of base, or you can use this log base command. All right, so we do log base 7, all right, of 50/50. And we get x is equal to 4.382. All right, do the same thing over here. All right, so we're going to get log base 12 of 1, 2, 3, 4, 5 is equal to x. All right, and just in case your TI-84 or whatever isn't quite working on your tablet at home, of course you can use the Calculate 84 app or whatever, but in case you can't find this log base command, all right, you can always do log of the argument, 1, 2, 3, 4, 5, divided by log of the base, which is 12. All right, and as you'll see here, that's the exact same answer as what you would normally get. Okay, so it's not super imperative that you have this log command if you can just remember the change of base formula. All right, so 3.791. All right, so you're really doing the same like math that we were doing on the non-calculator portion. It's just we get it to a point where our calculator can give us a nice decimal approximation. All right, same basic process here, right? We of course have to remember that ln is log base e. All right, write this in exponential form, and you get e to the 3.51 is equal to x. So then we get our calculator over here, and of course second ln is e to whatever power. So 3.51, 33.448. All right, same process over here, except now we're writing it in logarithmic form. So this would be, actually, we don't even have to do anything. This is way easier. All right, it's already in a form that's really easy for our calculator to deal with. All right, so we just say, okay, well, e to the negative 0.234. 0.91791. And that's it. Straight plug into the calculator. All right, so now we get to some word problems here. All right, Karen has $5,800 to invest. How much money would she have at the end of 12 years if the investment earns 3.2% and is compounded A, annually, B, quarterly, and C, continuously? All right, so A, annually, all right, we would say A is equal to P times 1 plus R over N, all to the NT power. All right, well, we're trying to find the final amount, so we're trying to find A. My initial investment here is 5,800, all right, times 1 plus the interest rate as a decimal is 0.032 over N annually. That just means one time per year, and it says at the end of 12 years. All right, so we go ahead and plug this in our calculator. All right, so we can say 5,800 times 1 plus the interest rate was 0.032. This is annually, so this is just 1. All right, and at the end of 12 years. So 7,000, or I'm sorry, 70, whoa. That looks way too, oh yeah, I didn't get the last part as an exponent. That would be y. To the 1 times 12 power. All right, so $8,464.17, round to the nearest cents with money, so 2 decimal places. Typically, normally I want you to round to 3 decimal places, unless the situation dictates, which money obviously dictates otherwise. So 8464.17. All right, so that's A. All right, B, we're going to use the exact same formula, except my N, which was 1, is going to be 4. All right, so very easy to just come over here. All right, you can just hit second enter, and it will pull up exactly what you just typed in. Go and change these 1s to 4s. All right, So $8,502.24. All right, and then finally C says continuously. All right, for continuously we use PERT. All right, so A is equal to, I still start with $5,800, e to the 0.032 times 12. So 5,800 times e to the 0.032 times 12. Bam. So we get 8515.24. All right, now notice that the more times per year you compound, right? Here's 1 time per year, here's 4 times per year, here's infinite times per year. All right, notice that the more times, the more interest you gain. Now, it's not a ton, all right? Just kind of, that's a way to check yourself. I see so many kids just type in one little thing wrong in a calculator on a test somehow, and like one of these will just be way different than the others, right? Like this one would be 80, 84, 64, 17. But then this one would be like $92,709.18. And then this one's back to 8515.24. Like if you get one of them that is way different than the others, you know you're wrong, right? So just keep that in mind when you're doing this type of problem. All right, how long would it take for an investment to double if it earns 3.1% compounded continuously? All right, remember we do have that double time formula, all right, which is just t is equal to ln of 2 over r. Remember that double here is the 2. If it's triple, this is 3. If it's quadruple, this is 4. All right, so in this case, we just say ln of 2 divided by 0.031. So ln of 2 divided by 0.031. 22.3595, so round this up to 0.360. And that would be years. That's how long it would take for that investment to double. All right. The size of a small herbivore population at time t in years obeys the function p of t is equal to 2300 e to the 0.51 t. If they have enough food and the predator population stays constant, after how many years will the population reach 10,000? All right, so we set the population equal to 10,000. All right, now we would divide both sides by 2,300. You could simplify this if you want. All right, so here you're going to have 100 over 23 is equal to e to the 0.051 t power. All right, so now this is an exponential form. You can use your definition of logarithm, all right, to rewrite this as log base e of 100 over 23 is equal to 0.051 t. All right, and then divide both sides by 0.051. All right, so we plug that into our calculator. So we can say, and remember log base e is just ln. So ln of 100 divided by 23. All right, and then we take all of that and divide it by 0.051. All right, so 28.817 years. And we are good there. All right, number 10, Susie will require $4,500 to travel after she graduates from college in 6 years. How much money should she ask her parents for now so that if she invests it at 6% compounded continuously, she will have enough money for her trip? All right, now do be careful here. A lot of students just automatically put this as the initial amount. No, this is how much she needs at the end. All right, so we're compounding continuously, so we're using PERT. This is how much she wants at the end, not at the beginning. All right, we're trying to figure out how much she needs to ask for now. Okay. Now this is actually a lot easier than people make it out to be. Remember, E is just a number, right? 2.718, da 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 da, whatever. All right. So if you take a number and raise it to some numerical power, it's just a number. So this is just P times some number. Well, how do you solve for P? You just divide by that number. I just went ahead and multiplied these. You don't have to do that. Right, so now this will cancel. So all you have to do is say 4,500 divided by e to the 0.36. So $3,139.54. So that's how much she should ask for now to have enough money when she graduates. And finally, half-life problem. The half-life of silicon-32 is 710 years. If 400 grams of silicon is present now, how much will be present in 2,000 years? All right, so our half-life formula, A is equal to P times 1/2 to the T over K. All right, remember this is our final amount. This is our starting amount, just like always. T is time in years, just like always. The only thing that's different is this K and its half-life. All right, well, it tells us what the half-life is, right? So we want to know how much is present at the end, so we're solving for A. All right, P, my initial amount, how much is present now, is 400 grams times 1/2. All right. Now, do be mindful that this silicon-32, right, that is a specific isotope of silicon. All right, those of you that have taken chemistry would be very familiar with that. All right, but that's just part of the name. That -32 is part of the name. Every year I have so many students that try to find a way to cram that 32 into this equation somewhere. It has nothing to do with it. All right, it's simply part of the name. All right, so it says that my half-life is 710. That means the denominator there is 710. It says how much will be present in 2,000 years. That's the time. Okay, so now we go ahead and plug this into our calculator. So 400 times 1/2 raised to the 2,000 divided by 710 years. And it would be 56.766 grams. All right, and that is it. All right. Does anybody have any questions or concerns? Go ahead and